Hi, everyone. Welcome back. We hope you had a good break and were able to enjoy some of the snacks in your basket. We're really looking forward to four talks from different researchers now across groups in MSR that cover a range of different topics. And each researcher will be talking for about 20 minutes. You can put questions in the chat channel, which the researchers will be able to respond to during the talks, but also we'll have a Q&A session at the end where we'll have a live question and answer with all four speakers. So the first of our speakers is Debadeepta Day, and he's from the RL group in MSR, and we'll be talking about efficient neural architecture search. So passing over to you now.
Good morning, everyone. I'm very excited to be here talking at the AI Breakthroughs event. Welcome. My name is Debadeepta Day, and I am a researcher in the Reinforcement Learning Group, which is part of the Machine Learning Research Area in MSR Redmond. I'm very excited to be here today talking to you about a hot topic in machine learning called neural architecture search and our latest algorithm. This is joint work with Sital Shah, Hanzang Hu, John Langford, Rich Caruana, and Eric Horowitz. Before we dive in, I will take a moment to introduce myself. I graduated in 2015 from the Robotics Institute at CMU, and my background is at the intersection of vision planning and reinforcement learning and controls. My journey in this topic started when I was visiting John Langford at MSR New York about 2 years ago, and we were somehow talking about DenseNet, and I put up the DenseNet architecture table on the projector. John immediately replied that he had no idea how these numbers came about and what to do about it. To be honest, I had no clue either. And this is the usual black magic involved in selecting an architecture even today. There is this process of trial and error, trying several different architectures, choosing magic hyperparameters like learning rate schedule, initialization, which can be very frustrating and also makes it appear that only groups with access to large compute can compete. Not only is this a frustrating process, we also have massive machine learning talent shortage in industry today. All these factors have led the community to focus on neural architecture search, where the goal is for computers to do this tedious task instead of us humans. Before we launch into the details of a specific method, I would like to present a very short overview of a rapidly expanding subfield. So this will be a 5-minute literature overview of over 500 papers being published, but don't worry. Every NAS algorithm out there has these 3 components. There is a search space, which defines the space of all realizable architectures. A search strategy to efficiently explore in this space, and often coupled with this search strategy is some performance estimation strategy where you're trying to figure out what is the performance of architectures which you haven't tried yet. Just to be clear, the central challenge in architecture search is that function evaluation is expensive. Sampling a point is expensive because a point is an architecture, and to evaluate an architecture means to go train it on the training set and find its performance on the validation set. In literature, you will find 2 kinds of search spaces. The first one is what is called as the cell search space or micro search space, where it is assumed that there exists an outer skeleton like DenseNet or ResNet, and the search space basically consists of finding cell templates that will be replicated as many times as are necessary. This has tended to be the most widely used search space mainly because it is much smaller and allows some human domain knowledge to be injected via the skeleton design. The macro search space is of course fully general, and it is what you would generally expect to encounter when you think of neural architecture search. And here we don't have any outer skeleton and cells. So the number of architectures that you can realize is far more. People tend to shy away from this search space because it is very large. This field is so hot that in this excellent continuously updated list of papers maintained by colleagues at University of Freiburg, I counted more than 200 papers in just 2020. Note there are still more than 3 months left. If you are interested in NAS and want to learn more about it, I will recommend starting from this excellent survey article, which is also periodically updated by the authors. The earliest paper on NAS actually goes back to 1989 from CMU. But this particular paper by Barrett Zoff and Quackley in 2016 really reignited the revolution. At its core, the method is very simple. There is a controller RNN which samples architectures and sends it out to a cluster to get trained in parallel. The results are fed back to the controller, which updates itself so that it is more likely to sample high-performing architectures. The update rule is the widely used reinforced algorithm, the canonical model-free RL algorithm. Here is a concrete example of how the controller RNN samples an architecture. It predicts parameters of layers, layer by layer, such as number of filters, filter height, filter width, stride height, stride width, etc. While this was a great first start, it took thousands of GPU hours to achieve reasonable results on relatively small datasets like CFAR10. This next paper cut down the search time from thousands of GPU hours to a single GPU day, far more practical. On both CFAR10 and PentryBank, ENAS achieved good performance while using orders of magnitude less search time. The trick that might appear barbaric at first glance is to use weight sharing amongst all the candidate architectures. Remember, the great expense in NAS is training each candidate architecture individually. By sharing weights amongst all candidate architectures and jointly training all of them, the cost of forward and backward propagation is amortized across all of them. One might wonder if this hurts since weights don't specialize to their own networks, but it turns out that there are some good multitask regularization effects since weights have to learn to be good across all networks that share them. Here are some examples of RNN cells learned by ENAS. Some examples of CNN cells. As you can see, the cells are pretty complicated and unlikely to be made up by humans. This last work we will look at before moving on to Petri dish is DARTS, short for differential architecture search. Unlike ENAS, DARTS does not use model-free RL, hence no controllers and has many nice properties. DARTS relaxes the discrete optimization problem in NAS to a continuous optimization problem using bi-level optimization. If you have heard of the meta-learning series of work by Chelsea Finn and others, DARTS is exactly the same bi-level optimization applied to architecture search. In this graph, nodes are tensors and edges are operations applied to parent tensors to obtain the next tensor. Say you have three operator choices. Example, conv 5 cross 5, max pool, identity to apply to a tensor. DARTS keeps them all around with weights over each operation. At the end of optimization, it picks the operator which has the highest weight to connect two tensors. This is how you obtain a final architecture. The search process utilizes bi-level optimization, which alternates between regular neural network training and training the weights on operators, often termed as architecture weights. For an in-depth, from-scratch tutorial, please refer to this video. Now we can dive into our method published last NeurIPS named Petri dish. We chose the name because we are growing networks from small to big, and the network decides how much capacity it needs automatically. There were a number of reasons for growing networks. As you will see shortly, it is a fully general method which can also deal with macro search spaces. It naturally incorporates new data as they arrive and exploits prior knowledge like human-designed models, which can be especially important in production scenarios. Petri dish is inspired by gradient boosting and directly searches the Pareto frontier or trade-off curve of flops, memory versus accuracy. Petri dish is also inspired by the earliest work on architecture search from 1999 named Cascade Correlation Learning Architecture. Petri dish has three phases. In the beginning, there is a tiny seed or parent model from which search starts. In phase 1, candidate neurons are evaluated to see if adding them permanently to the parent model will help increase accuracy. In phase 1, the candidates are not allowed to affect the original model's gradients and weights using some tricks that I will detail soon. The candidate with the highest weight is selected to be added to the parent model. Now let's look at phase 1 in a bit more detail. Imagine you have a simple model on the left you are starting out with. A candidate layer is evaluated by adding them to the parent network using stop forward solid black arrow and stop gradient dotted black arrow lines. Stop forward layer has the property that it allows gradients to flow through but does not allow forward activations to pass through. Stop gradient has the reverse property. This allows us to accumulate gradient of loss with respect to the candidate neuron without affecting the forward and backward flow of information in the parent model. If we decide to accept the candidate, then the stop forward and stop gradient layers are replaced by regular connections in phase 2. To amortize the cost of searching for exponentially many candidates, we utilize the same weight sharing trick you saw earlier and jointly train all candidates together. Here SG and SF refer to the stop forward and stop gradient layers from before. In order to select a sparse number of neurons, we impose a L1 regularization penalty on the architecture weights over each candidate and select the one which has the highest architecture weight. Recall we have 3 phases. To organize the computation on a distributed system, we organize these phases into queue or pools. Phase 0 is a pool of parent models which we are generating children from, and we will talk about how we are going to choose parents in the next slide. Phase 1 and Phase 2, candidate and children, are organized into queues that are resolved by worker processes. Every time a model gets trained at the end of phase 2, it forms a dot on this loss versus cost plot. We maintain a continuously updating estimate of the lower convex hull denoted here by the red line of this scatter plot. Since we don't know where exactly the Pareto frontier is, we wouldn't be having this talk otherwise, we maintain a small tolerance region around it, and only those models which currently lie on the Pareto frontier get to be sampled to go back to the parent pool. The assumption is that models which are currently far away from the current estimate of the Pareto frontier are unlikely to yield children which will lower the current estimate of the frontier. Let's see some results. But before I show you numbers, I would like to address a current crisis in NASland. We have a reproducibility and fair comparison crisis. In fact, it is nearly impossible to compare algorithms against each other due to differences in search spaces, the training routine that is used to actually train the model, hardware used. Some people may use V100, some people may use TPU, driver version, CUDA version, stochasticity in training on GPUs. But the community is working hard to establish standard benchmarks. And here are some links of standard benchmarks that you can refer to that we are trying hard to rally behind so that we can build reproducible, fair algorithms. Keeping in mind all the previous caveats, here are some results on both macro and micro search spaces. On macro search space, at the time of publication, Petri dish outperformed baselines in the same space using fewer parameters. On cell search, on micro search space, Petri dish gets competitive performance. On transferring models found on CFAR10 to ImageNet, Petri dish on macro search space performs competitively with even cell search space without having any domain knowledge injection into architecture design. So a big question that you might be thinking is AutoML solved? Is neural architecture search in particular solved? The answer is far from no. Still, lots of domain knowledge is injected into the process. Tricks and tips are needed for particular data sets in order to be state of the art. We also need better benchmarks. As you saw before, we are working hard as a community to come up with them. And major papers currently are stuck on CFAR 10, 100, ImageNet, and PentriBank. These are the marquee data sets that everybody reports results on. And we need to move beyond these data sets so that we are not overfitting to them as a community. And a thing which is also shrugged under the carpet are hyperparameters. It is assumed that there are some magic constant hyperparameter numbers which are going to be used to train a network once it is sampled by any mechanism. There is no fully general solution yet, but there are lots of useful successes that NAS has achieved. One thing I would like to highlight is that we have just recently released a new PyTorch-based library on GitHub with a permissive MIT license so that we can address this fair comparison and reproducibility crisis, as well as provide a turnkey solution to non-experts who are curious if NAS can help on their datasets but are overwhelmed by the fire hose of research coming out. If you want to try NAS for your problem, we encourage you to try it out and give us feedback via pull requests and GitHub issues. And now I would like to thank you all and open it up for questions. Thanks.
Thanks, Debadeepta. Great presentation. Just as a reminder, you can all continue to post questions to all of the speakers in the Q&A channel for the whole session. So please continue to add questions, and speakers that have already presented can answer those live, and then we'll have the Q&A at the end. So our next presentation is from Subho Mukherjee from the Language and Information Technologies Group, and this is on efficient learning for neural language understanding at scale.
Hello everyone, I'm happy to welcome you to the Microsoft Research AI Breakthrough event this year. My name is Subho Mukherjee and I am from the Language and Information Technologies Group at MSR. Today, I am going to give you a brief overview into some of our key research themes with a particular focus on resource-efficient learning to scale neural language understanding models. This is a joint work with my other team members, Amit, Guching, Sahar, and Wei, and a lot of wonderful work done by our summer interns over the years. The Language and Information Technologies Group at MSR works at the intersection of neural language understanding, information access and retrieval, and applied machine learning. Our core mission is to bring intelligent and trustworthy AI experiences to every person and organization in this world. This involves thousands of domains, hundreds of different tasks and languages, where the key challenge is efficient learning and inference at scale. But how much annotations do we really need for all of these different tasks? In general, if you consider so many different tasks, domains, and languages, and the cost of human annotation, this easily results in hundreds of millions of dollars. Even though you may have the budget, in many cases you cannot see or annotate these data due to compliance reasons, primarily dealing with sensitive user data. In this regard, our team has been heavily investing in these four key research themes. Scalable learning, how do we train massive deep learning models for hundreds of different tasks, domains, and languages with limited training levels, and I will give you a brief overview of some of our recent advances with few-shot learning and weak supervision. Knowledge distillation, to compress these massive neural network models to deploy them in practice with fast and scalable inference. Multilingual transfer learning helps us scale these models to hundreds of different languages with a particular focus on low-resource ones. And finally, interactive learning with human in the loop for course correction when the model makes a mistake. Last but not the least, we want to build robust and trustworthy models that provide fair and equitable information access to all. In the upcoming slides, I will give you a brief overview into each of these different dimensions, particularly focusing on scalable learning and knowledge distillation. To address the limited label data challenge, language model pre-training has been widely adopted in recent times for various NLU tasks. In this, deep and massive neural network models are trained in a self-supervised fashion over massive amounts of unlabeled data, and then fine-tuned on some task-specific label data for the downstream tasks. A number of large and massive pre-trained language models have been developed in recent times following this paradigm, ranging from BERT, Elmo, to our in-house Turing NLG and the most recently released GPT-3. Although these models have been widely successful in obtaining state-of-the-art results for a wide benchmark of NLU tasks, their huge size is a concern to using them in practice, with the most recently released GPT-3 boasting of a massive 175 billion parameters. Although pre-trained language models reduce the annotation bottleneck, they still rely on thousands of labeled training samples for fine-tuning on the downstream tasks to obtain the state-of-the-art performance. In this talk, we primarily focus on the aspects of scalable learning from limited labels and knowledge distillation for scalable deployment to address the aforementioned challenges. So let us first focus on scalable learning. In this, we want to develop techniques to obtain state-of-the-art results with the pre-trained language models while using only a few hand-labeled examples for the target task. For most tasks like text classification, sentiment classification, and intent detection, we have some amount of labeled data and large amounts of unlabeled samples to learn from. Self-training, as one of the earliest semi-supervised learning approaches, have been quite successful in these settings in recent times. In this, given a language model called the teacher, we continue pre-training the teacher model on the task-specific unlabeled data using masked language modeling objectives. This makes it aware of the domain semantics and vocabulary. Then we fine-tune the model on some amount of task-specific labeled data, apply the teacher model on the task-specific unlabeled data to obtain its logits. This we call the augmented data. This is used to train the student model. The teacher and the student model share parameters, and the above steps are repeated till convergence. There are also other ways of data augmentation like back translation, leveraging auxiliary resources like a neural machine translation system. Synthetic data in the form of domain-specific lexicons that we can use for distance supervision, as well as labeling functions as in snorkel style that can be used to improve the model performance in this framework. And all of these different areas remain an active area of research interest in our group. While standard self-training considers all the unlabeled samples, not all of them are equally useful for learning. In this work, we leverage Bayesian deep learning techniques to leverage uncertainty estimates of the teacher model for selecting samples that are most informative for the student model to learn from. We do it via a combination of three techniques. We leverage Monte Carlo dropout to obtain uncertainty estimates of the underlying neural network. Thereafter, we compute entropy to find samples that the teacher model is most confused about. And finally, confident learning to emphasize low variance samples for training the student model. In this text classification experiment on several benchmark datasets, we use BERT as the base encoder. The first and last column for each dataset shows BERT performance when trained with only 30 labels versus thousands of labels for the fully supervised setting. Our framework for uncertainty-aware self-training, which is the bar in yellow, uses only 30 labeled samples for each class for each task and obtains performance pretty close to the fully supervised BERT setting. This demonstrates the impact of unlabeled data and sample selection for self-training and few-shot learning. Finally, as we increase the amount of labeled samples for each task, the performance of the model also improves gradually. This summer, we have been working on extending some of the prior ideas for structured sequence labeling tasks, which is more difficult than instance-level classification tasks. Previous works a priori select a curriculum learning method for sample selection, like either using easy examples or hard examples to learn from. However, if the model already predicts samples with very high confidence, then there is little to learn from the easy examples, whereas hard pseudo-labeled examples might be just too noisy. In this work, we leverage meta-learning to adaptively select samples based on their gradient and the impact to improve the student model performance on a held-out validation set. Now we shift gear and move to other techniques to deal with limited label data, leveraging weak supervision. Many real-world tasks involve users and allow access to a rich set of user interactions with the system. For example, user utterances, clicks in an intelligent assistant, activities performed within a software, and so on. These user interactions can be leveraged to understand their intent better for many NLU tasks. In this work, we consider some task-specific label data and these weak signals coming from user interactions that are jointly leveraged to train a meta model and a main model. The meta model helps the main model to learn via sample curation and label correction. We develop Hydra with the following features. It can exploit signals from multiple weak sources of supervision like user clicks, utterances, and query refinement. It leverages meta-learning for sample selection as well as to correct the noisy labels. Additionally, to obtain a better training schedule, it leverages self-paced learning as a form of curriculum learning to select samples by their easiness to learn from. We apply these techniques to an interesting application for early fake news detection leveraging weak social supervision. Given just the text of the above claim, it is difficult to find out whether the news is true or fake. However, we can leverage the user discussions and social interactions in the thread to derive more signals as a form of weak supervision to train Hydra. While Hydra uses all the signals for learning, at test time, it uses only the textual content of the claim for inference. This helps in early detection without any social engagement that typically take a long time to accumulate. We apply this for fake news detection in two popular fake news benchmark datasets, namely PolitiFact and GossipCop. Hydra, shown as the topmost curve, performs better than other state-of-the-art methods including Snorkel. Also, the performance gap between Hydra and the other methods increase as you decrease the amount of clean label data to learn from. This is given by a low value of the clean data ratio. Additionally, Hydra learns instance-specific and source-specific weights for aggregating weak signals from multiple sources. Finally, we come to the last piece where I discuss on how to efficiently deploy these huge neural network models in practice. We do this via a method called knowledge distillation. Similar to the student-teacher training in self-training, here we adopt a big model like BERT as our teacher. It is used to produce logits and hidden representations on large amounts of unlabeled data that we call the transfer set. Then we train a smaller student model to mimic the teacher's logits and representations over this transfer set. We perform a multi-stage knowledge distillation operating over two different segments of the data. Task-specific optimization by optimizing the cross-entropy loss over labeled data, and the mimic learning over teacher logits and representations over the unlabeled data with three different loss functions. Multi-stage optimization for deep neural networks suffer from some typical issues like catastrophic forgetting, where the model forgets information acquired in the earlier stages. To alleviate this, we propose method to progressively update the model parameters by selective freezing and unfreezing of the neural network layers to obtain the best performance. We perform experiments for both text classification and massive multilingual NER over 41 languages. To summarize, our student model that we call Extreme Distill obtains massive compression with 35 times parameter reduction that is 90% smaller than the BERT teacher model while being 51 times faster. All the while it retains 95% of the BERT performance over 41 languages. Extreme Distill is already being used for several of our products and services. Now, to better illustrate how such a technique can bring massive infrastructure savings for real-life applications, consider the following hypothetical scenario. Assume there are 100 million users for a particular application where the user poses 10 queries per day. Consider 5 workdays per week in a year and average 100 millisecond latency for executing a query by a big model like BERT, and the GPU cost for using this model per hour. Now, Extreme Distill brings down this latency to only 2 milliseconds. If you multiply all of the above numbers, this overall results in $15 million savings in this single scenario, making huge pre-trained models affordable for all. Finally, to summarize, in this talk, I presented techniques to make NLU models scalable and accessible to everyone. I talked about learning techniques, leveraging few-shot learning and weak supervision from user interactions to scale these models to hundreds of different tasks and languages using only a few labeled samples for each task. I talked about knowledge distillation to massively compress these models and deploy them in practice with fast and scalable inference. We have ongoing projects to further scale these models to more languages in the world with a particular focus on the low-resource ones, where transfer learning plays a key role. In addition to this, we have also been recently focused on improving intelligent user experiences with human in the loop. This enables humans to further interact with the system in free-form natural language to guide the system. For example, given the natural language user query to find all locations with names containing a particular keyword, the system generates an incorrect SQL query as a response. The user can now step in and rectify again in natural language feedback of his earlier intent in order to correct the system. Finally, as we are deploying more and more of these AI services in real world, we need to be aware of its deficiencies and shortcomings. In this respect, we need to build models that provide a fair and equitable information access to all and does not discriminate against any specific group. We have some recent work in this space where we analyze gender bias in multilingual word embeddings and how it propagates via cross-lingual transfer learning. We propose strategies to mitigate this bias via alignment to gender-rich languages and provide recommendations on how you should use multilingual word representations for downstream tasks. This brings me to the end of my presentation. Thanks a lot for your attention and looking forward to meet many of you in the upcoming breakout sessions.
Thanks, Subho. We hope you enjoyed both of those presentations. We're going to take a short break now, and we'll be back again at 15 minutes to the hour, so that's 10:45 Pacific time. So go away, take a break, grab a drink, and we'll be back soon. Hi, welcome back. We hope you had a good break. So we have two more talks from researchers now before we move into the Q&A. Don't forget you can add your questions to the chat at any point during these sessions. So next up, we have Jina, who's part of the Human Understanding and Empathy group in MSR, and she'll be talking about her work on population scale study of human needs, which was performed during the COVID-19 pandemic and has some really interesting results and analysis and implications. Passing over to you, Jina.
Thank you, Daniel, for the introduction. My name is Jina. I work in the intersection of HCI, AI, affective computing, and human health and well-being. And I have this interesting role as both a research developer at MSR and also a PhD student at the University of Washington. And today I'll be presenting the work that demonstrates my dual role here. And I'd like to disclose that this work is currently under submission and is done in collaboration with Tim Althoff, who's my advisor at the University of Washington, and Eric Horvitz and Ryan White here at Microsoft. So many of the existing studies and data sets of the COVID-19 pandemic focus on the biomedical and epidemiological aspects of the case and fatality rates, including efforts in detection, infection propagation, therapeutic intervention, and vaccine design. However, it's important to keep in mind that although we may not all be infected by the coronavirus, we are all affected by the coronavirus. These challenges include societal issues such as disparities, economic issues such as unemployment, psychosocial issues such as stress, anxiety, and loneliness. And they remind us that even though certain public health policies may be effective in mitigating the spread of the disease, Pandemic-related policy decisions cannot be made on health information alone. Instead, we need to identify and understand the multi-level system of human needs and the impact of the pandemic and its associated policy decisions on these needs in order to inform how we can better respond to the pandemic and better prepare for future responses. So how do we go about understanding human needs? A standard way to assessing needs is through survey-based methods, but they can be costly and time-consuming to conduct or to gain fine-grained or real-time insights at large scales. Other methods, such as market research or analyzing purchase behaviors, can also provide insights about human needs, but they're often limited to consumer and commercial interests. E-commerce platforms such as Amazon or Walmart, or specialized service providers such as Talkspace for mental health or Coursera for education, may have access to large-scale real-time analysis of user behaviors, but they're often myopic to special needs rather than providing a holistic view of many needs. And public data such as Twitter has been used to characterize human needs, but again, they portray only a subset of needs that are externalized in public. On the other hand, our approach obtains signals about human needs by observing everyday interactions with a web search engine, in this case, Bing. And in fact, human needs are often expressed and fulfilled through seeking information or obtaining tangible support or material items on the web. And web search logs provide a glimpse into human behaviors in their natural states at large scale from data that's already routinely collected across a whole spectrum of needs and can be near real time with fine geotemporal granularity. So our data set involves a sample of web search interactions for the US population from Bing during the first 7 months of the years, 2019 and 2020. This included search query strings and the URLs of the subsequent clicks from the search results page, timestamp and zip code for location. And in total, we had over 35 billion search interactions from roughly 86% of the US zip codes. To understand how human needs have changed during the pandemic, we developed a computational framework to characterize human needs, which consists of ways to categorize human needs, and then ways to detect these human needs, and finally ways to quantify changes in these human needs. So first, our human needs categorizations were inspired by psychology theories. We were largely inspired by Maslow's hierarchy of needs, in that human needs can be categorized into broad categories that you can commonly see on the right. Physiological and safety needs at the bottom as your basic needs, love and belonging and self-esteem as your psychological needs, and self-actualization as your growth and self-fulfillment needs. And we borrowed from these needs and focused on 5 broad categories that can be extracted from web searches. And they are self-actualization, cognitive, love and belonging, safety, and physiological needs. And often in the context of Maslow's hierarchy of needs, the needs are thought of as mutually exclusive, but in reality, people can be experiencing multiple needs simultaneously. So we illustrate that by a ladder here. And for each of these high-level categories, we further subdivided them into needs subcategories, for a total of 79 need subcategories across 5 top need categories. And those 79 need subcategories typically follow the definition of the needs and the topics they include, which are shown here. Self-actualization needs are about realizing personal potential and growth through recreational activities, parenting, or weddings. Cognitive needs relate to pursuit of knowledge and intelligence, such as online education or educational degrees. Love and belonging needs are social emotional needs, such as relationship or mental health, social network or social activities. Safety needs stem from the desire to seek order, stability, and protection. So, for example, personal protection, finance, banking, job search, unemployment, and housing. Physiological needs, which are basic animal needs, examples include food, air, drink, shelter, and other body needs. So next, we extract these needs from search interactions. And a search interaction could be an expression of needs in multiple ways. It's a direct expression of a potential satisfier for that need. For example, a search query for toilet paper with a subsequent click on walmart.com could indicate a purchase intent that satisfies a physiological need. Or it could be a direct expression of the deficiency or satisfaction of that need. For example, pandemic anxiety is a direct expression of the deficiency of love and belonging need. And we match each search interaction to a corresponding need subcategory through simple detectors based on regular expressions and basic propositional logic. And once we're able to categorize each search interaction into one or more need categories, we then aggregated them across geography and time. And one thing to note is that we were also inspired by Max Neef's human scale development in that a satisfier, in our case, this expression of need, can satisfy multiple needs at once. Therefore, we allowed each expression of need to be tagged with multiple need categories. And we validated our detection logic using human labels from crowd workers for the top 5 need categories and achieved a precision of 97% using an example-based precision logic for multi-label classification. Now that we can detect and aggregate the needs, we proceeded to quantify the changes to these needs during the pandemic, and we took a common econometrics method of difference in differences to account for confounding effects between comparison groups. In our case, we accounted for yearly seasonal variations by comparing this year's needs against last year's needs, so matching January 2019 to January 2020. We accounted for weekly variations by matching day of the week, essentially aligning the days of the week between the 2 years. We accounted for variations in query volume by computing the relative proportion of the queries that expressed each need. Finally, the changes in the expression of need N between time 1 and time 2 is expressed as this equation here. In our case, T1 is typically before the declaration of the pandemic, and T2 is after the declaration of the pandemic. And we use the logarithmic scale to take advantage of the symmetric properties and the effect sizes that this form provides. Using this approach, we first asked, how did human needs change over time? We took the average daily needs during the period between January 6 to February 23 as the pre-pandemic baseline, and dates on or after March 16th to be post-pandemic period. Then we computed daily relative changes in needs, which you can see on the y-axis here, across all days in our data set, which you can see on the x-axis. And remember, with log base 2 scale, relative change of 0 means that there has been no change. Relative change of 1 means that the needs have been doubled. -1 means that the needs have been halved. And vertical dotted lines represent notable events. At a glance, all needs are elevated after March 1st, with physiological needs being most impacted. And to understand what contributes to these changes, we examined the subcategories. So physiological needs were primarily contributed by health condition related queries around the first reported COVID death in the US, followed by toilet paper and health measurement equipment purchases, reaching a peak shortly after the national emergency was declared in the US. And around the time of mandated lockdowns, we see an increase in cognitive needs through online education queries. Self-actualization, as well as love and belonging needs, slowly pick up, reaching a peak in April, and they're contributed by queries related to cooking and online social activities. Finally, after about a month since the pandemic, we see a sharp increase in safety needs shortly after the first stimulus checks were deposited, obviously contributed by stimulus-related queries and state unemployment site visits, as well as purchase of COVID-19 protection gear. Interestingly, we see a second rise of physiological and safety needs as COVID cases start to rise again in the US in early June. And this time around, what seems to be a reactionary increase in safety needs happened a lot quickly after the peak in physiological needs, which could be an indication that the population may be more economically vulnerable during this second wave. The next question we asked was, which needs changed the most? And to do this, we compared the average daily needs from the pre-pandemic baseline to the average daily needs from the first 4 weeks during the post-pandemic period. And we then sorted the needs subcategories based on their relative change between these two times. And when we look at the top 12 needs subcategories that increased the most, we see that most of them are physiological and safety needs, mostly on food, health, and economic assistance. And toilet paper purchase and stimulus queries reached well over 10,000% in increase, with up to 7 times increase in online social activity queries. When we look at these subcategories beyond the first 4 weeks, we see that unemployment and food assistance have not come back to the pre-pandemic baseline, indicating long-term socioeconomic instability. Online social activity queries also have not returned, indicating a prolonged social isolation. On the other hand, when we look at the top 12 needs subcategories that decreased the most, we see more self-actualization and other higher needs. When we look at the subcategories themselves, we see a pattern that these decreased needs are typical indications of positive or future outlooks, such as wedding, higher education, job search, life goals, and securing housing or rental. And it's worrisome that some of these needs remain below pre-pandemic baseline, especially for job search, which shows that those that are unemployed may not be seeking employment. So in general, we saw exponential increase in basic needs and troublesome decline in growth needs. Our next question involved understanding how differing policies may influence the needs differently. And to address this question, we looked at statewide shelter-in-place mandates, specifically the start dates and the duration, because each state varied in when they were in effect and their impact on needs related to social emotion and relationships. We looked at both short-term and long-term effects of the mandates. For short-term effects, we compared the needs 1 week before and 2 weeks after each state's shelter-in-place mandate. For long-term effects, we compared the needs from the pre-pandemic baseline with the last 4 weeks of our data set, so around July. We found that earlier shelter-in-place start dates correlated with more mental health site visits and fewer queries for online social activities, such as online games with friends or things to do with family online. We also found that longer shelter-in-place duration correlated with more negative mental health experiences and fewer wedding-related site visits or purchases. And this indicates that earlier and longer shelter-in-place mandates may have unintended consequences on social emotional needs, such as mental health. Lastly, we wanted to understand if there were gaps between the needs that are expressed on web search engines and the fulfillment of needs that are reported from other data sources. And we looked at 2 need subcategories, unemployment and domestic violence. We found that unemployment-related web searches closely matched unemployment claims reported by the U.S. Department of Labor. However, there are some discrepancies, most likely due to people being confused about how to file the claims. They have questions around eligibility or requirements, and they were being denied and having to file the claims again online. For domestic violence, many news outlets and research articles have reported increased risk for domestic violence due to increased physical and financial and social emotional stressors, as well as increased alcohol consumption at home instead of at bars. Disturbingly, we found that domestic violence queries decreased by over 20%, confirming many of the fears that victims are unable to reach out for help under constant surveillance by the offenders at home. And also, given that firearm access is highly linked to fatal domestic violence incidents, the increase in firearm purchase interest during the pandemic raises an alarm. So these exposed gaps between reported and expressed needs highlight opportunities for further investigation by experts in social work. So in summary, I've introduced a computational framework for quantifying the effects of the pandemic on human needs expressed through web search interactions. We found that basic needs such as physiological and safety needs were elevated, while growth needs such as self-actualization were subdued. Earlier and longer shelter-in-place mandates may have unintended consequences on social emotional needs. We also exposed gaps between reported and expressed needs, prompting further investigation into how to improve access to these critical resources. So where do we go from here? We think that there's an opportunity for leveraging changes in needs as an indication for a level of psychological and economic resilience and vulnerability. As we have seen in how the population responded to the pandemic differently for different needs, we need to understand how a community can endure social and economic distress and which communities are disproportionately and negatively impacted. We also think that changes in needs can guide efforts in preparing responses to future events and providing access to resources. Our analysis demonstrated that understanding the impact of differing policies or identifying the gaps between how the needs are expressed on the web and how the needs are reported in other data sources can help prepare adequate support and hopefully to reduce barriers and increase access to these critical resources and interventions. So for more detail that I didn't cover today, please check out our paper on arXiv. And thank you, and I look forward to your questions during the Q&A.
Thank you, Jina. Very thought-provoking presentation. Our final presentation for this session before we move to the Q&A is from Alekh Agarwal, and he's the manager of the RL group. He'll be talking about RL work and research at Redmond. Passing over to you, Alekh.
Yeah. Okay, so I'm going to be talking about a bit of an overview of the various ongoing research activities in the reinforcement learning group in Redmond, and this is meant to be a bit broad, but we'll try to get into some of the specifics as well. So just a quick primer and reminder on what reinforcement learning is about. It's an interactive learning process between an agent and its environment, where the agent repeatedly observes an observation or a state. We'll typically stick to the term state. It chooses one of available actions and observes a reward from the environment. And this process repeats many, many times, and the objective is to find a policy. Policy here is a mapping, a function that takes in a state and spits out an action. And the goal of the agent is to find a behavior policy that's going to maximize the sum of rewards it obtains over time. So just to ground this in an intuitive example, let's think about designing an agent that can do job scheduling for Azure. So the world we interact with looks like the population of various job requests that come into Azure. Our state would be some description of a candidate job. Our actions are potential machines where we can schedule this job, and the reward might be something we want to improve. We want jobs to finish fast, so it might be completion time. It might be cluster-wide utilization in terms of some appropriate metrics like packing density and so on. And we want to really optimize the overall health of the cluster over a longer time period. So the goal is to find a job scheduling policy that over time leads to smaller downtimes, better throughput, and other performance indicators generally being improved. The reason we are excited about reinforcement learning is, of course, it has a promise to transform just about every aspect of technology that we interact with in our daily lives. I already hinted at potential applications to network and computer systems through our running example. We can talk about potential use cases in healthcare, whether it's about personalized treatment regimes or a variety of mobile health tools to help us navigate our physical, emotional, and mental well-being in these stressful times. And finally, there is a a great number of potential applications in all kinds of user experience optimization, whether it's traditional recommendation system type settings or intelligent tutoring systems while everybody is getting their education at home. And I'm sure each one of you can come up with other potential applications that are ripe for the application of reinforcement learning. So it's useful to take a step back and ask, what do we need from reinforcement learning methods to be applicable to all these and more? And if I have to describe in a nutshell, I would say what we need are reliable and sample efficient learning methods that can optimize these long-term objectives we have, such as the cluster health or the health of a patient in healthcare scenarios and so on. And this simultaneous goal of reliability and sample efficiently entails a few challenges. So one thing we always worry about in reinforcement learning is this quantity called a horizon, which is roughly, you can think about it as how long the effect of an action lasts. And the longer it is, the further out in the future you have to plan in order to really take all downstream consequences of your actions into account. And unfortunately, the longer this horizon is, the harder it makes your learning problem, in that the number of samples we typically require to start behaving in a reasonable manner can increase exponentially with this horizon. Now, in many problems, you are used to working with lots of data, but in reinforcement learning, this can be a real issue because we don't really perceive our samples as a data set. We only collect them by interacting with the environment. And that means we learn about undesirable behaviors only when we try them out in the real world. And that can be a big obstacle in many settings. Finally, I'm sure many of you have heard great presentations and research articles about the high variance and instability that many typical learning methods exhibit in the quality of the solution they produce. And usually all these challenges are over and above some of the difficulties we face routinely in supervised learning relating to overfitting, generalization, and optimization, etc. Right, so these are some of the things we have to worry about if we want reinforcement learning to be applied in the real world. And in our group here, we do think about all of these challenges. Of course, I don't have nearly enough time to go into depth on all of those. So our plan for today, I want to give you some technical substance. So we'll do a bit of a deep dive into one topic of imitation learning. And then I'll go zoom out and give you a quick overview of many of the directions that we're currently pursuing. So imitation learning is a subfield of reinforcement learning, which stems from the realization, at least the version of it we're going to talk about today, that in real world applications, we usually don't start from scratch. We don't wake up one day and we say, oh, I have this problem and I'm going to solve it by using reinforcement learning directly. It's quite typical that practitioners have maybe tried other approaches to solving the problem before, perhaps by heuristics or by using supervised learning or other approaches. And while these approaches, got to a reasonable point, at some point the improvement stops and they want to go further using reinforcement learning. But these existing approaches can provide us with reasonable baselines that do something meaningful in the task at hand. So let's think about some examples. Suppose we were trying to design a reinforcement learning controller for an indoor greenhouse, then a pretty good starting point is actually just a rule-based policy that you might create by talking to domain experts on indoor agriculture. If you're trying to design an autonomous driving agent, this is really hard because we have a number of, apart from driving well, we just have a vast number of safety constraints we need to take into account, and enforcing all of them simultaneously can be hard. But if we take individual ones, like, okay, you should stop at a stoplight, you should follow speed limits, you should follow the lane, and so on. These are, we already see some of these things in commercial cars pretty broadly, and it's reasonably possible to have controllers that are designed for individual safety constraints. Satisfying them simultaneously is what's potentially challenging. Similarly, in the scheduling type example I talked about before, what we often have is we have a number of quality of service type agreements that we provide to the customers, and we need to perform good on all those metrics. And again, it's often easy to do well on an individual metric, but not on their entire combination. But in all these settings, what we see is we can have multiple baselines, such as for individual safety constraints, that do something reasonable, but don't solve the overall problem well. And also different baselines might work well in different situations. And in this way, they provide very useful domain knowledge that we can use to potentially accelerate the reinforcement learning process. And this is the intuition we try to leverage in the area of foundation learning. So the first thing is we do is pretty common in all of machine learning. We think about splitting the learning process into training and test phases, and we leverage these baseline policies often at training time to guide the exploration. And if you can have the baselines available even at testing time, then we can continue to use them into test. And the way you can use these baselines is to basically provide examples of useful behavior, such as having some basic strategies to prevent the crops from drying, or getting some candidates of safe actions in safety critical situations, and similarly in the quality of service example. Okay, so there are many situations where we have these available baseline policies. How do we use them? Let's start by thinking about what can we do when we have only one baseline, and this has been a very well studied area in reinforcement learning. And a rough caricature of how we go about behaving here is let's look at the caricature on the right. There's a reinforcement learning agent that is acting in the world, and it produces a sequence of interactions denoted as the states that were observed, the actions that were chosen, and the rewards that were obtained. And it then presents this interaction log to this baseline policy. And the baseline policy might tell, oh, I would have taken maybe a different action than the one you took for state S1 and S2 and so on. Right. And now, given this data, for instance, the simplest thing we can do is to just take the actions we've been provided by the baseline as labels and try to solve a supervised learning problem to behave more like the baseline. And this is indeed a well-studied idea in the imitation learning field, and works well if the baseline that you've received is a reasonably good policy. And at MSR, we do have a lot of work here in this area across the different labs, not just in Redmond, but also in Montreal, New York, Cambridge, and so on, including some of the first algorithms to some of the state-of-the-art approaches. But these are all only catering to the case of a single baseline, and often requires a single baseline to be quite good. So let's ask what can we do, going back to our original question, when we have multiple baselines and all of them are individually quite suboptimal, and different suboptimal baselines work well in different situations. Basic conundrum is when the learner is in a state and needs to decide what to do, it might receive conflicting advice from different baselines, and it needs a way to reconcile them. So in a recent paper, joint work with Xingan Chen and Andre Kolobov and the team, what we propose is we're going to try and figure out in any given situation, what is the best baseline, meaning which is the baseline policy that produces the best behavior, and we'll try to follow its advice. Of course, doing this is non-trivial. But also, because each one of these is individually suboptimal, we will not just stick to copying them. We will do some active exploration ourselves to find better behaviors and improve upon these baselines. And the precise way we do of doing this, we describe in our paper through an algorithm called Mamba, which first tries to constantly estimate the quality of each baseline policy at all the states the learner is visiting. And this quality estimation without guidance, but with the here, which is not really just takes a couple of steps and it falls down, and this because this approach and we have machine learning approach at the bottom right, and it does quite a bit. It runs, so it's not that it goes a bit further. It still falls down pretty quickly. Our algorithm Mamba, on the other hand, takes off, runs, and keeps going on and on and on. I want to point out in this particular experiment, we are actually using just one baseline policy. So this is primarily showcasing that the additional exploration that Mamba engages in really lets it significantly outperform the baseline policy and improve upon existing imitation learning, even in cases where existing imitation learning was known to do quite well. So for more details and experiments about how we also leverage multiple baselines in a meaningful manner, I encourage you to take a look at the paper. The archive preprint is included here. But in the interest of time, I want to zoom back out and point out that there are many other challenges we worry about in reinforcement learning, whether it's about sample complexity, safety constraints, a variety of adversarial perturbations, or just robustness issues due to distribution shift and so on. And we do worry about all of these and do research actively on topics ranging from exploration and representation learning, batch reinforcement learning, where there is no active interaction with the environment, notions of adversarial robustness for reinforcement learning, and so on. And unfortunately, I don't really have time to get into all of them, but I do want to highlight a few other areas of work. So one of the very successful ways of late of improving the sample complexity in supervised learning that we see is by learning generic representations that can then be applied and fine-tuned for respective tasks. Given that we are always worried about sample complexity in reinforcement learning, it would be natural to try and do the same here. And the hope would be that we can use, again, like in supervised learning, use this representation learning idea to successfully generalize across tasks as well in reinforcement learning. Whether we are thinking about the variations, small variations of a task, such as levels within a game, whether we are worried about related tasks, such as maybe two different games in the Atari suite, or even transferring from Atari to ProgGen. And the most ambitious and desirable would be if we can use this in a simulation to reality transfer type approach, where we maybe train the representation using lots of data in a simulated environment, and then use it to have sample efficient deployment onto a physical robot. So we've been working in these areas, also spurred by some recent work in the group on basic neural net architectures to better integrate transformers into reinforcement learning, and a lot of ongoing work on how to leverage that for better representation learning. Since I mentioned robotics there, we do have a bunch of interesting ongoing domains where we are trying to apply some of the reinforcement learning ideas to physical systems. Whether it is, so this is a pretty fun application, Azure data centers would love to automate a bunch of tasks related to maintenance, whether it's about flipping circuit breakers, replacing faulty hard drives, faulty cables, things like that. And can we automate some of these using reinforcement learning? Or completely differently, if you want to have a sailplane and do autonomous soaring without any human control and without any motorized support, how do you do that? So for more details, again, happy to answer any questions in Q&A, or for those coming to our group session tomorrow, definitely, we'll go more into the details of these. One final thing I wanted to highlight was a lot of the reinforcement learning research we see, the domains are very visual, right? So it's natural to ask what reinforcement learning should look like if our inputs, states, and outputs, actions, are both expressed in natural language. Matthew Hosconnect, one of the researchers on the team, has been leading up this effort on applying reinforcement learning in text domains, which obviously evokes conversation as an application. But simulating conversation is hard, so we study these things in interactive fiction games, which you can think of as something like Doom, but where you only see the description of the screen rather than the photo of the screen. And this entails a lot of challenges. Of course, we have to deal with enormously complex input and output spaces now, and on the output, the action side is really challenging. But we also have to worry about how to integrate things like common sense reasoning and knowledge representation into reinforcement learning now. And there's been some really exciting work ranging from basic platform development to agents that folks from the group have been involved in. Okay, so coming back to a high level, at a very high level, we are really excited about trying to bring the promise of reinforcement learning into the real world, and we worry about all the challenges we need to address to do so, whether it's about improvability of RL by leveraging domain knowledge, as we saw in the imitation learning example, whether it is about learning from cues beyond explicit reward feedback, which is particularly vital in representation learning type tasks, and certainly incorporating explicit rewards as efficiently as possible, which is kind of the topic of exploration that I didn't really talk about today, but many of us care about. There's this URL where you can go and learn more about the team and the members of the team and our interests, etc. And yeah, look forward to answering any questions in the Q&A panel. Thank you.
Thanks, Alekh. Great presentation. So we have another short break now for 5 minutes. We'll come back at 1:30, so it's 11:30 Pacific time. And we'll then move into Q&A panel session with the 4 speakers. So continue to put your questions in the chat, and we will ask those questions throughout that session. So we'll come back in 5 minutes. Thanks. Great, welcome back. And once again, thank you to all of our 4 speakers for their presentations just now. So we've got a panel session where we can ask Q&A to each of the speakers. And I'm going to start off by asking Jina a question. So this came through the chat from Maggie and was related to the causal understanding or causal reasoning you can do from your data. And perhaps, do you think that employment seeking may be reduced because of employment benefits? And sort of more broadly, causally related questions like that, have you been able to kind of find answers to those types of questions from your data?
Yeah, thank you for a great question. So in terms of the causal inference, so this analysis that we've done uses difference in differences approach, which has criticisms that it cannot make any causal conclusions. So with this current work, we are not claiming any causal relationships, but we are working on leveraging some of the techniques for causal inferences to make those connections. So it's coming. We're working on it. I think it's possible, but this work definitely has that limitation. And in terms of the employment, so what our goal was to really paint a broad picture of needs, understanding the fact that we're not experts in any one of these, subcategories or categories of needs, employment being one of those things that we're not experts in. But I did look in other research areas just to try to understand the landscape of why I'm seeing the kind of data that I'm seeing, unemployment going up, and then employment job search going down. And many other people have kind of studied labor force issues during the pandemic, including, the older generations. They're retiring early, therefore they're not seeking jobs. Other people have, anecdotally attributed things to the people taking advantage of the unemployment benefits. So I think there are questions out there that experts in this area can answer. Certainly, our goal is to try to raise these issues and bring, and hopefully that we can actually collaborate with people that are experts in these fields and try to answer these questions in more detail. But yeah, unfortunately, we don't have that expertise in-house. I think we have to go outside in order to answer those kinds of questions.
That's great. And another question from Tom. COVID is a particularly extreme example of an event. Could you explain more about what you've been thinking about how such analyses could be used in other cases, maybe other types of events, whether extreme or not? And how you might have to adjust your techniques if these events are more localized or shorter?
Yeah, definitely. We have another big event coming up in November. It's the US election. I think people have studied the previous election and they have seen impacts of the election on people's heart rates, mental health, and other kinds of things. So certainly we can do this for the election. There are other interesting things like daylight savings, for example, and its impact on people's, cognitive functioning. And we can actually see through people's search interactions or any other kind of telemetry through services on the changes in how people interact with these systems because of that 1 hour difference. So that would be another thing that would be interesting to look at. Certainly things like, Super Bowl or local disasters we can look at. I think the limitation is on, right now we're able to get data at the zip code level, but the really interesting questions that we want to be able to answer is by combining search interaction data with other external data sources like the census, like who are the people that we're actually gathering this data for, and what can we understand and how do we explain the data that we're seeing through kind of the demographic information that's external to the Bing search data. And that becomes the limitation, right? Like for things like local disasters, you need to start to understand like what are the available local resources that you have for the population that you're studying, and that those things are just harder to get access to. But if you have that information, then I think it's certainly applicable.
Great, thanks. Moving on to Alekh and Subho, you both talked about ways of sort of learning, self-supervised learning, so whether it's student-teacher methods or imitation learning from a teacher to a student. What are your thoughts on the limitations potentially of those approaches, maybe exaggerating biases? So if a teacher has a bias, will that be passed to a student? Is the same true in imitation learning, and does Mamba perhaps help address some of those issues or alleviate them at least? So yeah, what are your thoughts there?
Okay, you know, a lot of I guess a lot of little sub questions in that question. So let me start by talking about imitation learning and its you know, the role of biases there. So you know, absolutely true that you will reflect the biases of the teacher when you're trying to build on supervised learning, and supervised learning at its core suffers from the same issue without kind of building in some guardrails for fairness into the underlying supervised learning techniques we are using. But that's also a plus, because we are using the supervised learning techniques where people have been working quite a bit about incorporating fairness considerations, so we can hopefully leverage some of those ideas much more directly. But also, there is the nice aspect in some of these approaches, in particular like Mamba, because they're trying to not just copy the baseline, but really improve on the teacher. If at least the reward signals you have are such that they prefer the less biased behavior overall, then you can hope that the agent might discover them. There is really no way of saying at the moment that the agent will discover them for sure, but thought at it. Of course, you know, they're like building reward functions that will capture or downplay our bias itself is pretty tricky in general. So I don't want to somehow plan of you know, making things less biased just down to the reward design problem, because that's not really solving it either. So in short, we are definitely not you know, actively addressing that problem at the moment, and it might be an interesting direction to pursue.
Okay, thanks, Alekh. With regards to natural language understanding, we see that sample selection plays a very important role. So we really kind of need to know which are the instances on which the teacher is confident on versus not so confident on. That was our kind of main or core idea behind this uncertainty aware estimation, where we kind of leverage the low variance samples that are coming from the teacher, that is the ones that they're most confident about, and only passing them through the student. So obviously, in this process, we do prune out some of the noisy predictions from the teacher, and the student model is able to outperform the teacher in certain cases. But yeah, we also do pass on some of the biases where the teacher might have overfit to the student. And in these cases, as Alekh pointed out, we need to build other guardrails regarding some kind of semantic consistency constraints or other kind of consistency constraints based on the task that we are going to solve in hand.
Great, thanks. For Debadeepta, a similar or related question from Eva about one of the charts you showed in your presentation about lower gender bias in languages that have different words or grammar for different genders, such as Spanish. could you explain more about that? Eva was wondering if you might expect that biases would be larger in such a situation.
Okay, so Daniel, I think that question might have been for me.
Oh, sorry.
I was talking about, yeah.
Mm-hmm.
So in English, like you have 2 genders, and in Spanish, you have 3 genders. So in most of the gendered languages, what we do in our work is we project the semantic representations into different gendered subspaces. So as you have more number of genders, we are able to kind of tease apart these different biases that are geared for different languages. For example, if you were to take a language like, for example, say German, which also have more than 2 genders. And if you were to kind of do some kind of transfer learning where you are projecting the semantic representations to English, which have kind of 2 genders, then you kind of combine the biases that are coming from multiple genders to only 2 principal units, principal directions. On the other hand, if you were to project them to Spanish, then you would see the different biases on the different principal components, like 3 principal components, more clearly. So that is, I think, the core idea of projecting the semantic representation to different gendered subspaces, where we see that the bias decreases as you project them to a language containing more directions for the different gendered subspaces.
Great, thanks. And so moving back to Debadeepta, sorry for that. So there was a question in the chat from Tom about the contrast between neural architecture search and MAML. So just drilling into that a bit more, personalization is obviously a huge thing in machine learning. You want to ideally have models that are adapted to specific individuals. Do you have any? Could you share more about any work you're doing in terms of personalization of models, and then how that might be done efficiently? For instance, if you wanted to adapt an architecture of a model on a device and not do that in the cloud, or not do that where you need to share data across a network or devices?
Yeah, absolutely. Yeah, that's a great question. The recent algorithm that we just proposed and which is also now in Archive, our platform, which is getting shortly released and already on GitHub. One nice property that we tried to pay a lot of attention to is this ability to do Pareto frontier search, where you are, so oftentimes what happens in the real world, you don't care about performance at a particular number of flops or multiply adds or memory occupied by your architecture only. You care about the entire trade-off curve, so that imagine you are serving, you have a web service, and your web service has access to, let's say, cloud GPUs, which are pretty big, right? Like, you have access to V100 GPUs. So there you can have very easily a very nice 300 megabyte model, which you can load and serve very fast. But for reasons of cost and efficiency, even there you may want to lower your bill, because a V100 costs a lot more per hour than, let's say, an old M40 or even CPUs. And the other thing is, you may want to trade off what you want to do, let's say, on the cell phone or on device or on IoT edge versus what you do in the cloud. And there's this really nice spectrum of constraints that can come in on memory, flops, etc. And ideally, you would want an architecture search algorithm to not just give you a single point answer that this is the architecture you use if you have a V100, but this is the architecture that you might use if you have, let's say, an iPhone grade cell phone, or this is the architecture on which you want to do things on device. And here's the trade-off, right? Look, an iPhone grade device will never have the accuracy that maybe you will be able to get on a V100 with a very large network, right? And but you may be able to see how much of that is acceptable to you and trade off in one search alone. But you run, our hope is that you take for your data set, you run Petri dish, and you come up with a gallery of models, and then you can choose which one to deploy where without having to run search again and again for every constraint. So that idea of directly searching the Pareto frontier is a what we believe is a very powerful thing to have in a feature to have in a search algorithm.
Great, thanks. A question for Alekh. So a lot of RL is done in simulation, especially when you think about safety critical scenarios, you might need to simulate those for certain reasons. But can you talk about what you think are the sort of the challenges of moving from simulation to the real world, and what the differences are, limitations of simulation and advantages of it?
Yeah, that's an excellent question. So, hit the nail right on the head. There's obviously lots of challenges that arise when trying to do reinforcement learning directly in the real world in safety critical settings, which is why we don't see that as something happening every day. Certainly starting from simulation and trying to do simulation to reality transfer is a natural thing to do there. And one of the ways people try to guard against running into unsafe situations there is by doing a lot of basically perturbations to the simulation to make sure that the agent is trained in environments that give it sort of robust coverage against simulation errors, right? So there are tricks called things like domain randomization. You might imagine that training a robotic agent in simulation, you'll make sure you perturb environment variables like friction and how contact forces behave, things like that. Things like imitation learning to again provide some viable candidates for safe behavior, and also thinking about actively incorporating constraints into reinforcement learning algorithms, which is something there's been increasing amounts of recent work on, as well as reasoning robustly from offline data that we've collected, which basically is its own kind of simulator, are all very important techniques that are being increasingly developed in this area. That said, ensuring safety during training and reinforcement learning certainly remains an ongoing challenge for the field, and something we very actively think about and have been, putting papers out on even very recently.
Great, thanks. Another question coming back to Jina. Na-Young was wondering if you could elaborate a bit more about the propositional logic subcategorization of the needs that you did, and the process. How did you do that subcategorization and the process to get there?
You'll be surprised. It's so simple. It's just simple regexes and patterns that we identified that would fit into each of the categories. So actually, I didn't discuss this too much in the talk, but for each kind of a high-level category, let's take unemployment, for example, there are two kinds of matches we could do. So we had a list of unemployment sites, like the government sites. Each state had different sites that people can go to apply for unemployment. So we took kind of like the base domain URL and try to match the subsequent clicks to the domain URL. So that's one way of doing it. Another way to look for unemployment signal is to look at the query string and see if they have mentions of job application or unemployment, being laid off or things like that. There are other things that are more purchase related. So toilet paper, for example, like I said, you have to type the things that you are looking to buy, but also it has to be followed by a clicks into one of the e-commerce domains. So we had a list of somewhere around 61 domains popular domains that we've identified from being search queries as e-commerce websites. So those define like a purchase subcategory. The regular expression and the logic is really just looking for, this word is followed by that word, or for experiential queries, we're looking for things like I'm alone, I feel depressed, I am anxious, or games with friends, board games with family. So very simple things, and that was on purpose. You could probably spend days and weeks and months trying to build really good classifiers for each of these subcategories, but really wanted it to be simple and intelligible, and also optimized for precision. And we're looking at the changes and looking at all of the data simultaneously using the same logic. So we thought this was a great first step. And obviously, if for things that we're more interested in down the line, we may move on to a more complicated, more complex way to detect some of these signals.
Great, thanks. Taking a step back, we all experience that research is not necessarily a linear process. So that involves a lot of iterations. Involves serendipity. Sometimes you kind of come across ideas that yesterday were far from your mind, but really help you overcome some kind of hurdle that you're facing. And I was just wondering if any of you had examples related to the work you presented where such a thing happened, where whether it's collaboration with other people or being in an environment where you can be creative and explore ideas helped you kind of overcome those.
I guess I can go. So yeah, I mean, I think certainly. Actually, one of the hardest things about this extended work from home has been the absence of a lot of those serendipitous interactions where you talk to a coworker, learn about their work, and you get an idea about how it might actually be immensely beneficial to something you could do. But definitely, in my own research and for most of the people I know at MSR, we tend to be extremely collaborative exactly for this reason that just having inputs and ideas from a broad group of people can be so powerful. And certainly for the particular work I went into a bit more detail today on imitation learning. So there is a question that had been bothering me really since 2015 when I did some previous work on imitation learning on how to simultaneously how to really improve upon the a suboptimal baseline policy well. And it wasn't until we started thinking about combining multiple baselines, we landed on a solution concept and a method that did a pretty good job on solving that challenge as well, which wasn't really something I had started out with an idea to solve. And all the credit goes to having an amazing creative intern who came in with a very determined attitude, went through the breakthroughs experience like many of you, and now works in the office next to mine. So definitely those interactions end up creating a lot of value for us.
Okay, maybe I can give a slightly complementary perspective as well. So as Johannes mentioned in the morning at MSR, we are not only kind of collaborating with all the researchers, but we also kind of talk about many of the problems that are out in the real world for the different products and services that our, say, partner teams are working on, like the product teams. So one of the problems that we started out or like worked on last year was a knowledge distillation that typically kind of came from them. Like you have these big models like BERT, and then you cannot kind of have that latency to kind of productionize them. Then what do you do about that? Similarly, another work on this few short learning that also came from a similar kind of problem perspective, that you have a lot of customer data that you can't really look at, which is kind of compliant and user sensitive, which we call like eyes off, but you kind of can see some proxy data, which we call eyes on, that are typically kind of voluntarily contributed, right? So how do you build models and how do you kind of mitigate the distributional shift? And all of these different kinds of problems are kind of motivated by existing real-life problems in the products and services, and we kind of collaborated with both the researchers internally and our partner teams to come up with solutions.
I just want to add one more thing to that, which is for me or for our group, I think one of the ways for us to be creative and think outside of the box is to collaborate with people who are really beyond our domain of expertise. So, for example, we typically work with clinicians. So we had a psychologist that we worked with to develop one of the mental health applications. We work in domains of health and well-being, which means we don't have the clinical experience, but we can partner with other clinical institutions who can bring in that expertise that we don't have. So I think a lot of those collaborations and seeking outside of your group for expertise that you don't have, I think is really valuable.
Great examples. Thanks. Question for Debadeepta. I'm aware that you've done some work looking at kind of architecture search in the context of pipelines for interactive systems. Could you explain a little more about that? Because I think that's a really nice example of kind of interdisciplinary or cross-disciplinary engagement, thinking about the real-time systems and how they might leverage some of what you've been doing.
Oh, absolutely. Yeah, that's a wonderful question. So that actually also ties into the previous question you just had. The whole problem definition of, okay, let me first actually give a little bit of the problem. So the problem often is that we have systems, meaning we are a software company. The world runs on software in many ways right now. And we have this incredibly complicated software pipelines, not just machine learning pipelines, but generic software pipelines, right? And ask anybody who has done anything with regards to machine learning in a real world software production pipeline, they will tell you that the machine learning bit of it is actually the really minor part of it, right? The entire pipeline and everything else that it fits into matters. And so, for example, imagine you get a query and the query has to go through a lot of steps and components. And then what decision you make at each component really matters for the downstream component. For example, if you have a face recognition module, which receives the image, it finds where the most likely faces are, sends it to, let's say, a face landmark detection module, and then which processes it, and then maybe it may send it to an affective sentiment detection module, and so on and so forth. So every decision that is getting made by a previous component has repercussions for what the downstream component see. So we saw this that this abstracted out problem as pipeline optimization problem, where this can happen for anything, not even just machine learning pipelines, but in general software engineering pipelines. So and they were creating this frameworks, and which is our platform for situated interaction, which is this wonderful platform for writing these right? And you can, if you look at any reasonably simple pipeline, there are actually easily components in complicated structure, and oftentimes you have to do trade-offs, especially in real-time systems. That hey, if I spend a lot of compute here in this part of the pipeline, I will not be able to have enough compute to do this other thing I'm free. And it is a matter of how quickly you make decisions. Then we saw this. What happens in the middle steps, and we just wrote the first paper at AAAI this past year. But we have barely started scratching this wonderful problem. How to do sequential decision, and how to adapt to it as every example comes in, where it comes in. Where do I allocate compute parameters. And then we realized that this is actually also like if you think about hyperparameter tuning, you can think of pipeline optimization as dynamic hyperparameter tuning. Like you are tuning parameters of the system as you are looking at the state of the pipeline and as you're looking at inputs coming in. And this is again like where we will benefit not just Microsoft, but just everything out there. And again, this is really the hallway conversations and talking into your colleagues' offices and hey, what are you working on? Or what is that about? Right? That's the most wonderful part of working at MSR.
Great example. And just to wrap up, one final question, segueing from that. So Pavel had a question, recognizing the real benefit of removing the burden of low-level model tuning using architecture search. But do you think that these methods will be able to do the harder things that humans currently do? Things like discover batch norm is a very useful thing to do, or different types of activation functions, create a transformer. You know, will we get there, or is that something that always will need a human to kind of develop those insights?
Well, I'm glad that's a wonderful question, because there's actually actively in the community papers coming out where people are designing, like, hey, if I design a search space which admits, let's say, like, 10 to the power 18 different activation functions can be realized. Or you could even think of this as a continuous parameterization of an entire family of activation functions. And you want to figure out, like, which activation function the network should use automatically in which part of the network, right? And as it is searching for, it should not only search for, let's say, what layer types to put in, but it should also automatically search for what activation functions you should put in. Now, obviously, this comes with a caveat, right? Like, you are expanding the search space. The search space becomes bigger and bigger. And there's this trade-off between how expressive and general I want to make the search space, and hope that, like, really interesting things will fall out in reasonable compute time, where reasonable may mean, like, let's say 1 week on a 8 GPU machine, and reasonable will vary from what is the application and how much money you have for compute. But at the same time, we are starting to see, like, for example, there's work finding, like, very interesting new kinds of activation functions, which we would not have found before by hand, or at least like, unless you, maybe we would have, like, it's hard to do counterfactuals here, but we are definitely finding computers are finding very interesting activation functions. Now, talking about things like transformers or batch normalization, which you can think as a little bit higher level concepts. One thing that people are finding is that hey, what if I take a architecture space in which transformers is a dot, right? Like self-attention is a particular point in that architecture space. Would self-attention emerge, right? Like, and would, like, maybe like hybrids of how much self-attention you need combined with how many encoders and decoders you need, would all of those things automatically emerge instead of us, like, trying things out by hand, right? Like, and if you look at transformer paper or BERT paper, at least when I look at it, and I'm not even, like, in the deep learning things as much, I'm always scratching my head. Why is it 6 encoders? Why is it 6 decoders? Why is this connected there? What happens if I connect this there? And to me, a lot of these, like, higher level building blocks, we can bias the search space, right? Like, we can take the search space, but instead of us trying to decide how many decoders and encoders there are, let a computer figure it out, right? Like, why should we humans do all this tedious work of typing things in a configuration file? So I think, and bigger changes will come about. Like, hopefully we will discover new families of transformers. We haven't yet.
Great, thank you. So that brings us to the end of this session. Thanks once again to all the speakers for your great presentations and this Q&A. We now have an hour-long break, and we'll be back at 1 p.m. Pacific time. And we'll have another fireside chat directly followed by the poster session. So grab a break, some food, and we'll be back with you at 1 p.m. Thanks.